What's going on, guys, and welcome back to the channel. Today we are going to be talking about, in all honesty, probably the most important part of your laboratory build out, and that is going to be distillation. It is just the theory today. Application will be coming in the next video, probably next week, so definitely check out both. That way you have the knowledge and the understanding coming in the future and the wisdom to pay attention to all of these videos that are teaching you A to Z what to do in your laboratory. You already know, guys, got quite a bit to cover today. So without any further ado, let us go ahead and dive right on in to the content. And just as aforementioned, this is the distillation portion. I am Grim from WKU Consulting, so let's talk about it a little bit. Distillation is a powerful purification technique that does drastically increase the purity of a botanical extract. Distillation can be simplified as the act of purifying a liquid by selective evaporation and then recondensation. This purification process is implemented by heating the input material until target compounds are evaporated and then pulling the resulting vapor through a chilled condenser. It is condensed back into its liquid form and then collected. Distillation carries excellent utility in separating compounds in a mixture when there is a great enough difference between their boiling points and or their vapor pressure. The key part here, when there is a great enough difference. I remember it was FUD, and I still hear a bunch of FUD in the laboratory environments these days that, if you dial things in just correctly, you'll be able to separate CBD, Delta 8, and Delta 9 all by distillation if you have them all in the same conglomerate mixture of crude oil. And that is just incorrect because the compounds between the three boiling points are similar. Very similar. And you'll understand more what I'm talking about as we go through the theory here together. But anybody who tells you that, that's a red flag. That is a rookie. Do not believe them. You cannot do it. Vapor pressure or equilibrium vapor pressure is the presence of vapor in thermodynamic equilibrium within its condensed phase inside a closed container. When a liquid is confined to a closed container, an equilibrium exists between its liquid and its gaseous phase. This equilibrium exists regardless of the temperature inside the container or the liquid because some particles within the liquid, essentially at any temperature, will always have good enough energy to escape the intrinsic cohesive forces and enter the gaseous state. When distilling an impure mixture of compounds like that found within a botanical extract, the various constituents contribute to the overall vapor pressure of the liquid depending on the concentration of compounds within the solution and their respective boiling points. The vapor pressure of a solution is affected by temperature alone and is not a function of volume or surface area. As the temperature of a solution increases or decreases, so does its vapor pressure. During the distillation process, when the temperature and the vapor pressure of a compound have increased past the ambient pressure of the closed system it is within, a compound will transform from a condensed state to a gaseous state referred to as evaporation. So that closed system that we're talking about could be the orb on your rotary evaporator. It could be the boiling flask in your short path distillation apparatus. It could just be a beaker on a hot plate. Equilibrium vapor pressure is an indication of a liquid's evaporation rate. It relates to the tendency of particles to escape from their condensed phase into the vapor phase, which can be observed as boiling. When a liquid is boiling, its vapor pressure is equal to or greater than the ambient pressure within the closed system containing it, causing the compounds to evaporate from their condensed state. The rate at which those compounds are evaporated is determined by vapor pressure, which is a function of the temperature exerted upon its liquefied state and the ambient pressure of the closed system that it must overcome. What do you use to aid in dropping that pressure? Vacuum pump. The evaporation of compounds happens at different rates depending on the vapor pressure of each constituent. Compounds with the highest vapor pressure tend to evaporate from the solution first as heat is applied during distillation. Compounds evaporate from the solution in order based on their atmospheric boiling point as heat is applied. So for instance, when you are distilling cannabinoids, you will obviously notice the terpenoid fraction coming off first, closer into the main body portion of the compound coming off second, and into the tails portion. All of these are directly correlated with the information that we're giving you here. The highest compounds with the highest vapor pressure and the lower boiling points in atmospheric temperatures and atmospheric pressures will tend to evaporate first, and then so on and so forth as you make it through the compound's range. Compounds with similar vapor pressures are commonly evaporated and condensed at the same temperature range, making it challenging to isolate compounds in some instances completely. CVD, Delta 9, Delta 8, very difficult as they all have generally a closer temperature range and a closer vapor pressure range, especially under vacuum. Typically, compounds within the same temperature range are evaporated, condensed, and collected into what is called a fraction. These fractions are typically divided into three categories: the heads fraction, containing the compounds that evaporate before the target compounds; the main body, containing the desired target compounds, all of our money; and the tails fraction, containing the compounds that evaporate after the target compounds. When it comes to evaporation, for a compound to undergo a phase change from a liquid to a gas, it needs to overcome the ambient pressure within the system. Think of ambient pressure as omnipresent weight pushing down at all times. The greater the ambient pressure or the atmospheric pressure, the more energy in the form of heat is needed for those compounds to evaporate. Let's take a look for this instance at the boiling point of water. You can see the higher that we go, the less temperature, the less ambient pressure is needed to evaporate a compound. The closer we come to sea level, the more temperature. The further we go below sea level, again, the more vapor pressure and the more temperature needed to evaporate the same compound. The boiling point is the temperature where vapor pressure equals the atmospheric pressure. This can be observed when boiling water at different elevations or atmospheric pressures. Atmospheric pressure is the weight of the atmosphere exerted on the Earth's surface, typically measured with the barometer. At sea level, where atmospheric pressure is greatest, barometric pressure is about 14.7 psi under standard conditions. There is less atmospheric pressure at higher elevations, resulting in reduced resistance to evaporation. As a result, water is observed to boil at a lower temperature at higher elevations. It requires more energy in the form of heat in order to boil at sea level due to the increased atmospheric pressure. And also, the level of vacuum that you're able to achieve in your vacuum pump or whatever you're doing, whether that's your vacuum oven or so on and so forth. You might notice, a lot of these days, a lot of the vacuum pumps have the exact same kind of monitoring system. They're all going to have the ammonia filled vacuum gauges, which will be right around, negative 28 millibar, negative 30 millibar will be probably the best that vacuum will go. You will notice as your as your sea level increases or decreases, you'll be able to pull a tighter vacuum or a deeper vacuum than you normally would at, let's say, if you were under sea level. If you're in the mountains of Colorado, for instance, your vacuum pump is going to work really, really well because you're going to have less atmospheric pressure to deal with at higher elevations, like we just discussed. By reducing the amount of ambient pressure exerted upon a compound, we can drastically reduce the amount of resistance a compound must overcome to evaporate. While energy in the form of heat is still necessary to trigger evaporation by reducing the pressure within the system, by pulling it under a vacuum, the amount of energy in the form of heat necessary to induce evaporation is reduced. The most efficient way to reduce pressure within a closed system is to pull the system under vacuum with a vacuum pump. Vacuum can be considered negative air pressure or pressure measuring below atmospheric pressure. Air pressure is defined as atmospheric pressure or the pressure within a container due to the compression of gases. When a system is pulled under a vacuum, the air pressure is evacuated until no air or gaseous volumes remain. This reduces the amount of pressure a compound needs to overcome to evaporate. When pressure is reduced, it in turn lowers the threshold of vapor pressure needed for a compound to evaporate, escaping its liquefied state into a gaseous state. So just like if you were to travel further and further and further and further into space, where you would have a perfect vacuum and zero, atmospheric pressure whatsoever, the higher that you get or the deeper that you get to a absolute vacuum, the lower the heat or kinetic energy you will need to force a compound to reach its boiling point. This is beneficial when distilling botanical compounds because heating a botanical extract near the atmospheric boiling points of its target compounds for prolonged periods can induce degradation, in some instances, especially with cannabinoids. By applying vacuum to our distillation procedure, we can reduce resistance to evaporation and the amount of heat needed to evaporate the target compound from a botanical extract, accelerating the process. Vacuum can be achieved to a varying degree depending on the strength of the vacuum pump and the design of the distillation apparatus, with non-restrictive flow being ideal. Also, in your rotary evaporator, it's the exact same concept. Using a vacuum pump to decrease the barrier or to decrease the atmospheric pressure also helps you sort through a lot more solvent a lot faster. This would also be considered distillation. You would distill the solvent in your rotary evaporator, and then you would recondense the solvent over a condensing column, returning it from its gaseous state to its liquid state, where you could then collect the purified solvent for reuse later. And so obviously bringing things under a deep vacuum, decreasing the atmospheric pressure that it has to overcome to reach its boiling point, helps with maximum efficiency. Vacuum is measured with any set force per area units. In the customary U.S. system, vacuum is measured in inches of mercury, abbreviated Hg, the atomic symbol of mercury. This measurement is determined by using a mercury barometer by measuring the distance traveled by a pull of mercury up a tube when pulled by a vacuum, with the maximum level of vacuum measured as 29.9 inches of mercury. Within the context of distillation, through a vacuum pump, the entire distillation apparatus is pulled under vacuum, reducing the ambient pressure of the system, which in turn reduces the resistance to evaporation and the amount of vapor pressure needed to achieve the evaporation. The continuous operation of the vacuum pump through the distillation process also assists in pulling the ensuing vapors from the evaporator to the condenser portion of the distillation apparatus. Condensation is the other half of the distillation process. Condensation is defined as the conversion of a vapor or a gas to a liquid. Condensation is initiated by the formation of molecular clusters of vapor within a gaseous volume. Condensation occurs when a vapor is cooled or compressed past its saturation limit within a given volume. Molecules within a vapor are typically far apart from one another. As more vapor collects within a given volume of air, it becomes saturated with vapor. This increase of density or closeness of vapor molecules increases the tendency of the molecular clustering of vapor, resulting in condensation collected as a liquid. The saturation limit of a gaseous volume is the maximum amount of a vapor a given volume of air can contain. The saturation of a gaseous volume can be achieved via either evaporation or cooling. Evaporation achieves saturation of a gaseous volume by increasing the level of vapor in a given volume. As more vapor collects within a given volume, that volume reaches its maximum vapor capacity and is considered fully saturated with vapor. Conversely, cooling can be utilized to reduce the saturation capacity of a gaseous volume and reach its saturation limit. Similar to the saturation of a solvent, a gaseous volume has a reduced saturation capacity at colder temperatures. Since a gaseous volume has less saturation capacity at lower temperatures, cooling can be utilized to reach a gaseous volume saturation limit and induce the molecular clustering of vapor and condense that gaseous vapor back into a recoverable liquid. Now you must be asking, well, if colder temperatures allow the recondensation much more rapidly or decreases the saturation capacity, then why do we not run the Liebig condenser at super cold temperatures? And that's a wonderful question. That is because the oil that you are recondensing, becomes viscous or thick, and then it will not flow down the Liebig condenser and empty into our collection vessel where we need to collect it to be able to, package, sell, collect our fractions, so on and so forth. So that is the reason. But you are correct. Running a cold Liebig condenser definitely would help in, increasing the ability to reach saturation limit much faster and induce molecular clustering. However, then the oil would not move. It would just brick up in our Liebig condenser, and what we did save in time by cooling faster, by saturating faster, we would lose in waiting, probably forever, because our oil would just never run down the path. Okay. Based on the principles of psychrometry, the vapor's condensation point present in a sample of air can be defined as the temperature at which the vapor changes into a liquid. The temperature value that allows this process is referred to as the dew point. The dew point of vapor is the temperature at which vapor will condense out of its gaseous phase into the liquid phase. Dew point. Do you understand the dew point? In the context of distillation, vapor does not need to be chilled excessively to initiate condensation. Generally, any temperature at least 40 degrees Celsius or 104 degrees Fahrenheit colder than the temperature at which the compound evaporated is sufficient in recondensing a vapor back into a liquid. During the condensation of a vapor into a liquid, as the vapor cools, the gaseous volume reaches its maximum vapor capacity or condensation point and condenses into a liquid. In doing so, the latent heat is released by the vapor and transferred to the surrounding environment. In the context of distillation, the heat is absorbed by the transfer fluid of the condenser. A distillation condenser is typically a jacketed portion of the distillation apparatus or a little coil inside of such, in a tube and shell type setup, circulated with chilled fluid, creating a lower temperature portion of the unit where vapors can be condensed back into a liquid form. The condenser cools the ensuing distillation vapors down, slowing their movement, initiating a molecular clustering of vapor and providing a surface for vapors to condense on. As vacuum pulls the distillation vapors through the condenser, the recirculated fluid absorbs the heat from the vapor, thus reducing its saturation capacity beyond the condensation point, resulting in the condensation of vapor into a liquid. The resulting liquid formed during the distillation process is referred to as distillate. Solvent recovery, right? In any distillation process, it would be referred to as distillate. Do not think of distillate as just some oil to be smoked. The condensed distillate flows down from the condenser into a collection apparatus. Once the desired target's compounds have been distilled, the result should be a highly purified extract containing upwards of 90% if you're in cannabinoids and 98 to 99% if you're talking about solvents of the target compound. This highly pure extract can be used to make a variety of different products, reused in your solvent recovery process, or used as an input for further isolation of the target compounds. Yes, so that is the theory or the knowledge portion of this version of, WKU extraction training. So you can understand why you're doing, or you can know what you're doing, and the understanding will come into why you're doing it or how you're doing it in the next video, which we will go over. So definitely stay tuned for that one, because we'll be talking about short path distillation apparatuses as well as scalable wiped film distillation apparatuses, how to assemble them, how they are utilized, different parts and things to consider when putting together your laboratory, especially full bore, the little tube, cost is everything. But we're gonna go into a deep dive with that, as well as an SOP that you can use that will get you through just about every cannabinoid distillation that you can think of, as well as much of the solvent recovery portions that you might need as well. And once again, in the distillation process, when we covered the solvent recovery, that is a form of distillation in the previous video. So I digress, but definitely you want to stay tuned for the application portion, because if I put it all together in one video, it would be 2 hours long, and we don't want that. Guys, I hope that you found this video helpful and informative. If you like this video, I have no doubt that you will like one of these popping up over my shoulders, and in the YouTube playlist section, you will be able to find, they're all labeled different things, catchy titles for you to enable you to you know the YouTube algorithm to put them out. However, if you go to the playlist section, you will be able to see a playlist called Extraction Training A to Z. And from there, you will just start at the first video and you will follow them through, and it should give you almost everything that you need, maybe minus some experience, but definitely everything that you need to get started conceptualizing and probably even find you a job where you can get your foot in the door to understand what you're doing, maybe on your own or, working for somebody else. But definitely go through each one and every one of those videos. There's a lot to unpack there. There's a lot of theory and a lot of science. So unpack it all, rewatch it a couple of times, save it, and utilize it as a baseline, for your education. Because new people are coming online that is enabling us to, go to college for this type of thing. But it's still not a thing yet. So, this information is what you can use as a case study, as a university level case study for what we are doing specifically in cannabinoid science. And I hope it blesses you. See you in the next video. Peace.